All right, section 1.1, we're going to continue our discussion of some of the terminology that we're going to be using in all of the rest of the semester for trig, and we're going to look at different types of angles. Now, we had left off last time on this definition about what angle measures are in terms of degrees. They're 1/360th of a revolution around a circle, and that 360 degree kind of a rotation is used all kinds of places. You probably heard it used in the Olympics if you watched anything in terms of gymnastics or diving. Usually you see those there. And you'll see it used in like esports, right? When people talk about skateboarding, right? Doing certain kinds of rotations. And then we talked about it in terms last time of a car rotating. So if you spin your car 360 degrees, I don't recommend that. But if you do, it means you spin it all the way around. So that's what we're talking about when we're talking about degrees. And there's 4 types of angles that we're going to look at. There are other descriptions sometimes used as well, but this is the ones your book uses, and they're the pretty standard ones. So an acute angle is an angle that's between 0 and 90 degrees. A right angle is equal exactly to 90 degrees. An obtuse angle is between 90 and 180. And then a straight angle is 180, and it's better known as a line. So when we're looking at these angles, I'll draw a picture of each one to give you a reference. So an acute angle would look something like this. A right angle, looks like this, and is typically, though not always, marked in the corner like that to let you know for sure that it is. When in doubt, ask, and I can let you know whether that's intended or not to be a right angle. An obtuse angle looks like this. And then a straight angle, that's a typo. I don't know why that says that. We're going to see typos this semester. Should say that it equals 180 degrees. I'm so sorry. And so it looks like a line. So when we mark the angles, we often mark them with these kind of curving sort of notations. You can even do it here if you wish. And then this is showing you that it goes here all the way around. So we have a line. The one that was written in here, it shouldn't have even said 270 to 360, but if it's bigger than 180 but less than 360, there is another name for it. It's sort of the outer part of this. It's called a reflex angle. Your book doesn't focus on that, so it's not something that we'll really refer to, but there is a name for it. All right, so taking a look, then we're going to remind us some features about these graphs. So a standard position for an angle is that the vertex is at the origin and the initial side, thank you, did everybody get the seating chart? We're all good. And the initial side is along the positive x-axis. So the sketch looks something like this. Let's change colors. How about yellow? So it looks like that. The vertex is at the origin, and the initial side is down here on the positive x-axis. This is called standard position. It's not that other positions are not, usable and we won't see them. This is just the one we will typically see. Now, everything inside of this diagram has some names that we refer to, and so we want to make sure that when I say them and when you say them, we mean the same thing. So this right here is our x-axis, and this is the positive x-axis, or you can put a plus. This is still the x-axis, but it's the negative x-axis, or you can put a minus. So it's the negative side. I have a child in my house that keeps flipping them around. Obviously, that creates some problems if we don't use them in the same way. So there's just a standardized way that we use them. This is the y-axis, and this is the positive y-axis. And then this also down here, going straight down, is the y-axis, but it's the negative y-axis, negative part of the y-axis. As I mentioned before, this along the positive x-axis is my initial side if it's in standard position. And this one over here is called the terminal side. And if we measure the angle upward. We talked last time, this angle theta, we often use Greek letters. This would be a positive angle. Okay, so positive goes counterclockwise. That may seem a little bit sort of non-intuitive. The reason that our coordinate axis does this sort of a feature is because when it was created by someone who was left-handed. And they went around the circle in a counterclockwise way because of the way that they wrote. So that's kind of a fun fact. Over here, we have another diagram just because I didn't feel like I could fit everything on one. Not because it's really different. I just want to put more information on it. So this top quadrant right here on the left is called quadrant 1. If we go counterclockwise, this one is called quadrant 2. And Roman numerals are used for these typically, though it really doesn't matter, but just so that you're aware. This one is called quadrant 3, moving again counterclockwise, and then we have quadrant 4. Using this sort of a picture along with these description of angles, I promise I'll flip back in just a second, we can actually talk about what kind of angles end up residing in each of these quadrants. So in quadrant 1, our angles go between 0 and 90 degrees. That's the picture of this yellow one that I had drawn over here. Is it's an acute angle. It's between 0 and 90 degrees. If our angle goes clear over into quadrant 2, then we're between 90 and 180. If we fall down in quadrant 3, we're between 180 and 270. And if our angle goes all the way around and extends into quadrant 4, then our angle is between 270 and 360. So when we're talking about an angle, we'll generally have a picture in our mind, or we start to develop a picture in our mind of where we are sort of in space. So if somebody says you've got a 200-degree angle, you need to be able to sort of think through where is that living. That angle lives its terminal side in quadrant 3. Okay? Now we're going to come back to this diagram in a minute, and we're going to put some other details on it, but this is good for now, and we'll move forward. When we actually end up on one of the axes, those are called quadrantal angles. So the quadrantal angles have a terminal side along the axes that don't have the equals, right? I said it was less than 90, and then I said it was greater than 90. It was less than 180. It was greater than 180 in different quadrants. Well, if we actually equal 90, 180, or 270, we have it along one of the quadrants. It's a quadrantal angle. Now, you need to be really careful. Your calculator has the ability, if you've got at least a scientific calculator, of doing things in radians and doing things in degrees. We've only talked about degrees so far today, but we mentioned radians. I think, did we mention radians last time, or did we not yet? We will get to the radians part. So radians is a measure that's done a little bit differently. And we need to make sure that we are using the right type of mode at the right time. So if you do have a TI 84 or 83 kind of calculator, I can show you where you can change it. Okay, so let's do that real quick. Grab your calculator out. If you don't, if you've got a scientific calculator or a different kind of graphing calculator, whatever, that's fine. You might have to play around with it to find it. But if you're using a TI 84 or 83, if you click on mode, you're going to get a screen that's got a lot of different options. And the third one from the top, at least on mine's an 84 today that I have with me, says radians or degrees. And you can just change the highlighting on which one you're on at whatever time you're using it. Okay? So we're going to go back and forth between radians and degrees as we work with this. We'll get to radians on the next slide. Central angle. A central angle is the positive angle whose vertex is at the center of a circle. So that's the definition for central angle. It's typically the angle in standard position that we keep talking about. Okay? So, radians then. A radian comes about when we talk about the rays of the central angle that intersect the arc of the circle. If the radius is equal to the length of the intersected arc, we say that this measure equals 1 radian. So let me draw you a picture. Here's my circle. If you take this out here, right, that's the positive x-axis. And if you were to measure, this is called 1 radian. We'll call it 1 centimeter, 1 inch, 1 foot. It doesn't matter. It's 1, right? It's a measurement of 1. If I were to take this length and I were to sort of think about doing it in string. If I took a string this long, and then I measured the string along the outer side of the circle so that it's the same length, so that these are the same, right? So this is the mark from geometry where you make things the same. They're equal lengths. Then this right here, this angle that's created in the middle, would be called 1 radian. Okay? We call it 1 radian because the radius is equal to the length of the arc. Okay? That's what a radian is. Now you might think, well, why can't we just use degrees? It's so much easier. The reality is that after trig, it is not so much easier to use radians. And everything that we do in calculus and beyond is done in radians. It's not easier to use degrees, is what I meant to say. It's done in radians. Everything in calculus is done in radians, and it is a lot easier. It's just not comfortable because you have used degrees a lot, and you've used radians maybe none at all thus far. So we're moving into using radians because they will make your life a whole lot easier later. This is kind of like for, if you haven't gotten to this point yet, you will as well. Decimals are not friendly to use. Fractions are much friendlier. They're a lot friendlier in mathematics. But if you tell that to my 10th graders, they would just look at you like you just jumped off the moon. Aren't you crazy? That sounds dumb. Decimals are so much easier. And they are easier in certain contexts, but as you move on in mathematics, they're not. And this is one of those kind of things too. Degrees have been great up till now. We will continue to use them, but we're going to introduce the idea and use the idea of radians more and more. So I want you to go back to this diagram over here now. We're going to add to this diagram more details than we had before. The details we have right now are all in terms of degrees, right? I want to put them on there in terms of radians as well, because we're going to see radians showing up, and we again need to know where are we in terms of radians. So in the top quadrant, the first one, quadrant number 1, this one actually goes, our angle measure goes between 0 and pi over 2. That's the radian measure. Okay. And then if we go over to quadrant 2, we go between pi halves and pi. Down here in quadrant 3, we are between pi and 3 pi over 2. And over here in quadrant 4, between 3 pi over 2 and 2 pi. So again, in terms of quadrantal angles, I didn't write it on here before, but we will now. We'll try to use yellow and see if it's readable enough. This right here is 90 degrees. That's thick. Hang on. At least that part of it's not readable. Can you read the yellow okay? It's not too bright or anything? Okay. And in terms of radians, it's pi over 2. So the quadrantal angle that's occurring at 90 degrees is the same as the angle called pi over 2 in terms of radians. Over here, we're at 180 degrees, which is pi radians. Down here is 270 degrees, which is 3 pi over 2 radians. And if you go all the way around, you've gone 360 degrees or 2 pi radians. Now, you've seen pi's used before. You've seen them used in some formulas along the way, and you probably didn't even sort of realize that you were using radians when you were thinking about it that way. You saw them used in finding things like the area of a circle or the circumference of a circle. Usually happens in middle school somewhere. So we've used pi's before, but now we're going to use them in a much stronger way. Okay, everybody good so far? We have yet to do a single example, but today is the day. I know. All right, so right here. This question asks, I don't know why the directions are not on there, but they're on your paper, to classify as acute, right, obtuse, or straight. Okay, so that there's no work to show, right? Like you're just going to look at it and decide which of those quadrants are you in, which of these angles is it a type of angle for, right? If you match it back up over here, which do we have for each of the measures that we're given? All right, so here we are, sorry. Good grief, one more. 177. 177. What type of an angle is it if you have 177 degrees? It's obtuse. And what type of an angle if you're at pi over 3?
Acute.
That's acute. Now, if you're not comfortable or super willing to work with fractions right away, and you're thinking, well, how do I know that pi over 3 is actually less than pi over 2 or bigger than pi over 2? You can always turn it into a decimal, right? Pi over 2 would be 1/2 of a pi. This is 1/3 of a pi, right? So you could actually turn pi over 2 would be the same thing as 0.5 with the pi. And pi over 3 would be the same thing as 1/3, which would be 0.3 repeating of a pi. Well, 0.5 is bigger than 0.3, right? So you can think about it in terms of decimals as you work your way up to sort of using the fractions more consistently. So yes, it is acute. All right, so what I want to show you then is how we go back and forth really between radians and degrees, and then degrees and radians. What do we do to go back and forth between? So conversion between degrees and radians. If we want to go from degrees to radians, we will multiply by pi over 180 degrees. And if we want to go back and forth between radians and then get it into degrees, we're going to multiply by 180 over pi. Okay? So both of them is a multiplication. It's just we're multiplying by this equal measure. Now, why is this? Well, these values are equal to each other. 180 degrees is exactly the same as pi. They're just different measurements, right? It's like talking about 12 inches and 1 foot. It's the same amount, yes? 16 ounces and 1 pound, same amount, right? So if they're the same amount and I multiply by it, I'm actually multiplying by the number 1, right? And somewhere back in Algebra 1, you learned that you're able to multiply by the value 1 because it doesn't actually change anything. It's just changing how it's expressed, right? So that's actually what we're doing here is we're multiplying by the number 1 because 180 degrees and pi radians are exactly the same amount, just in different units. This is a unit conversion is what all really it is. So we're going to do some examples where we're going to convert them. So same directions as on your paper. Again, I don't know, my slides obviously didn't get pulled in quite right. We'll go back and fix those later. We're going to convert. Your directions actually on your paper. We're going to go from degrees to radians on this slide. Okay, so it gives us 18 degrees. It gives us negative 315 degrees. And we're going to be doing number 1 here because we're working from degrees into radians. So it says that I'm supposed to be multiplying by pi over 180. So I'm going to multiply this by pi over 180. Now, the answer will have a pi in it. So we're not using the pi button to change something. It's still going to have a pi. We're just trying to simplify the fact that we have 18 in a numerator, right? This is like 18 over 1, and 180 in the denominator. And if it is one where you notice something just, sort of simplifies very nicely, then you're welcome to do that. If it's one that you don't see something simplifying very nicely, you're welcome to reduce it with your calculator. I don't care. This one's probably pretty straightforward. 18 and 180 both divide by what? 10. They both divide by 18, and I'm going to get a 10. Yeah. So if I divide this 18 by 18, I get 1. And if I divide 180 by 18, I get 10, right? So this ends up being pi over 10. Now, grab your calculator, if you will, because I want to show you if this were an ugly one, or maybe you'll want to use this on problem 4. I want to show you how your calculator can also assist you in turning, these kinds of fractions into simpler pieces. So we know that we're going to end up having 18 over 180, so we're going to use this sort of as a trial run. So just type into your calculator 18 over 180. And it's going to give you a decimal, probably 0.1. Did I do that? Okay. If you want to turn a decimal back into a fraction in your calculator, it's really quick and easy. And I'm talking about a TI-84, but all the rest of the scientific ones will do it. You're going to hit Math, the Math button, and the first option on it says Frac. If you hit that, it will take the previous answer and turn it back into a fraction of 1 over 10. Right? We're not interested in recreating the wheel and me teaching you how to reduce fractions. That's not what we're doing in this class. So if you want to use your calculator to change decimals into fractions, go for it. All right, so that's turning this back into a fraction. It does give you that this is 1 over 10, and then you would have the pi still a part of the answer. All right, so let's do the negative 315. So again, we're multiplying by pi over 180. So the answer is going to be bigger than 1 because 315 is bigger than 180. Now these will reduce. You could divide them both by 5, right? You could do that and you could reduce things down. But again, if you would like to use your calculator, you may. So it's 315 divided by 180. The decimal is 1.75. And turning it back into a fraction is 7 over 4. So you have a 7 over a 4. We usually put the pi on the top with the 7. You could also put the pi after the 7/4, so you could write it as 7 over 4 with a pi here. Either of those would be perfectly fine. So we do want them written in fractions. We really don't want them written in decimals. Even if my math lab allows you to put it into decimal form, it's not going to be super user-friendly later on, okay? So this is 7 pi over 4. To give you a decimal approximation, because it tells you the directions as well, leave the answer as a multiple pi, and then it says round to 2 decimals. So rounding to 2 decimals means taking this answer and finding the approximation. So if you take then your calculator and you do pi divided by 10, it's going to give you 0.31415926654. That's what mine says. But it just says round to 2 decimal places. So we're using regular rounding rules. This is approximately 0.31, which is the secondary part of the directions. If I do this one, 7 pi over 4, I get 5 point, and then it says 49778. So since it says 497, the 7 is going to round this up, so I'm actually going to get 5.50, right? Because the 7 is going to round the 9 up to a 0, 5, and so forth. So I have 5.50 and 7 pi over 4. Some directions will tell you to leave them in pies only. Some will tell you to turn them into decimals. Some will tell you to do both. This is how you do it. Now we're going to go the other direction. Oops, I'm sorry.
What happened to the negative?
Oh, I lost it. I shouldn't have. Thank you. Let's put it back in. I should have a negative. You bet. Put a negative on all the things. Thank you. I thought about it, and then once I got into the calculator, I completely forgot about it. Yeah, you're not going to be able to move forward and allow the calculator to do that with you. This should say 3 and 4. I don't know why it says 5 and 6. Okay. I do think I'm missing my 5 and 6, though, so that's exciting. All right, we'll just do it on the same slide. On your paper, 5 and 6 ask you to turn radians into degrees, right? Paper's right. My slides are wrong, but your paper's right. So we're going to go from radians. I didn't say that right. Yeah, I did. Radians into degrees. And the first one that you have listed is 2 pi over 3, correct? Awesome. 2 pi over 3. So to do 2 pi over 3 from radians into degrees, we're going to multiply it by 180 over pi. Now you'll notice this one, the next one, we're going to see something a little bit different happen. Most of the time, when you start with a radian, it's going to have a pi in it. That's just how we usually see them written, probably 90% of the time. So the pi's actually cancel out. And everything else means we're going to multiply like with fractions, right? So I have 2 times 180 divided by 3. If you want to multiply across the top, you've got 360 over 3 then. And then divide, this is 180 degrees, so let me put my degrees on there. What is 360 divided by 3? That's 120. So this is a measure of 120 degrees. Okay, so that's pretty straightforward. There are times when there's not a pi in the radian amount given. So this number 6 is an example. It's just -4. We still multiply 180 over pi. What it really tells you, though, is that you're not going to have a nice whole number kind of an answer for your degrees. It's going to look kind of ugly. So we're going to just let the calculator do all of that for us because it wants us to round to 2 decimal places in the directions if we have to round something off. So we're going to do -4, which I'm not going to lose my negative this time, -4 times 180, and then we're going to divide by pi. Again, your calculator will allow you to do that. It is -229 degrees. And then I have some decimals. It says 183. So rounded to 2 decimals, it would be 1/8. And there's my degree measure. It could have you round the decimal here to just a whole number of degrees. That would be a legitimate kind of a question. It could just be 229 degrees. Okay. All right, any questions on those going back and forth between the two? Do make sure you put the pi and the 180 in the right place. If you flip it around, you're going to get the wrong answer. So if something feels kind of funny, if pi's aren't canceling, things like that, maybe double check that and that you've got those in the right place. All right, on this one, it wants us to actually draw the angle approximately in standard position and then to state which quadrant we're in. It's not wanting us to convert anything. Now, could you convert to double check if you're feeling more comfortable with degrees versus radians? Well, of course you could. But the goal is for you to start getting more comfortable and knowing where things are without that. Okay? So this one says 3 pi over 4. So if I am at 3 pi over 4, 3/4 is bigger than 1/2, right? It's bigger than 1/2. So at 1/2, I would be up here, right? I would be right here. This is 1/2. I'd be at the quadrantal angle, vertical right there. So if I'm going to go bigger than 1/2, I need to move over here like this, right? But it's not all the way down to a whole pi. So I'm going to look like it's going to look something like this. So this is approximately the graph that I'm looking for. So from here to here is approximately 3 pi over 4. And where does my terminal side end? What's the name of that quadrant over there? Quadrant 2. Okay, negative. We've got a negative angle happening on the next one. So we mentioned it last time, but we haven't really talked too much about it today. Positive angles go counterclockwise, negative angles go clockwise. So I've got to come from my initial side. Initial side's still going to start here. These are supposed to lie right on top of there. I'm afraid you won't be able to see it very well, so mine are looking a little bit high, just so you know. So this one, I'm going to come down here like this. If I only go down to the bottom, where it's the negative y-axis down here, how far have I gone? I've gone -90. So in degrees, this would be -90, right? So I got to go more, but if I go all the way over here, I'm at -180. So I've got to go somewhere in between. Again, it's a sketch. We just want to make sure we're in the right sort of general location. So we're down here. So this right here would be -140 degrees. And what quadrant did I end up in? Yep, quadrant 3. Now, if I can go both positive and I can go negative and end up in different quadrants, then there's got to be a way to sort of describe what happens when I end up in the same place. So, for example, on this one, if I go down -140 degrees, that's the same thing as going positive something, right? There's a way to get there the other direction, too. Not only that, but if you think about it in terms of sports, right, these spins and these rotations that people have done, that you've seen them do or so forth, if I take where I am right now and I go 180 degrees like this, that'd be the same thing as going all the way around 360 and then 180 more, right? So there's ways to represent, multiple ways to represent each one of these locations where my terminal angle ends. And all of those are called coterminal angles. They just mean that the terminal side is in the same place. So these are two angles with the same initial and terminal side, but they have possibly different rotations. So, for example, if I went, actually, let me just use the 140 we did before. So down here was -140, right? What would I have to do if I went in the positive direction to get to the same location?
Take 360 and take 140 out, you can find the angle.
Excellent. So what's 360 minus 140? 220. So if I went this direction, 220, I would also end up at this same terminal side. So what we would say is that 220 and negative 140 are coterminal angles. They have the same initial side and the same terminal side. But that's not all of them. If I add another 360 to this, or subtract another 360 from this, and I go around again, and I go around again, and I go around again, I get infinitely many coterminal angles. Okay, so coterminal just means they have the same initial and terminal sides. So there's lots of different places where I could end up with different angles, but the same location in terms of the coordinate plane. So taking a look at an example, if I have a negative 150, this one wants us to find a positive angle less than 360 or 2 pi, whichever one is given in, that's coterminal. So what did we do with the negative 140 when we ended up getting 220? How did that happen? We added or subtracted 360, right? So if I have negative 150 degrees, and I'm looking for a coterminal angle, what am I going to do? Subtract it from 360 or add 360 to it, right? That's the equivalent description. So if I add 360 to this, which is the same thing as 360 minus 150, what will I get? 210. And it meets the criteria of the directions. The directions said positive, it's positive. Less than 360, it's less than 360. Okay, so 210 is coterminal with negative 150. 25 pi over 6. I purposely chose something a little bit awkward. All right, you're welcome. All right, so we've got 25 pi over 6. It'd probably be a good idea to pause for a moment and ask yourself, 25 over 6. What is that approximately? How big is that number?
It's a little bigger than 2 pi.
It's bigger than 2 pi. Yeah? It's bigger than 2 pi. So if it's bigger than 2 pi, instead of being like negative like the last one, instead of adding 2 pi to it, I'm going to subtract 2 pi from it. So this is minus 2 pi. Now, again, how can you use your calculator if you would like? Well, you can use your calculator and just have it do 25 over 6 and minus 2. Okay, you can have your calculator do that. If your calculator is super unfriendly in doing so and you wanted to actually do it the same way, right, you're trying to do this by hand, you need the denominator to be a 6. So if we have 2 over 1 and I want to turn it into something over 6, what is it over 6? It's 12. This is 12 over 6. And if I subtract 25 over 6 minus 12 over 6, I'm going to get 13 over 6, which is still bigger than 2, right? So what do we have to do? Same song, second verse. Do it again, right? We're just going to subtract another 2 pi. So we're going to do it again. In essence, I'm just keeping a tally of what we've done on the top here. I'm going to subtract another 12. That's terrible notation. Let me start over. We're going to take our 13 over 6, and we're going to subtract another 12 over 6. But it's going to be really nice this time. What are we going to get? 1 over 6. Okay, so in the end over here, I get 1 over 6 pi, or simply pi over 6. Your calculator is perfectly able to do what we just did. Just type in 25 over 6. It's going to give you 4.16 repeating. And you can subtract 2. That gives you 2.16 repeating. So you subtract 2 again. Now this is a decimal 0.16 repeating. That's between 0 and 2. We're at the value we want. If this is an unfamiliar fraction to you at this point, you can simply hit math frac, turn it back into a fraction. It's 1 over 6. Okay. If I'm moving too quickly through using some of the features for your calculator, just see me after class and we'll find out where it is in your calculator because I know not everybody's got the same one. So the coterminal angle that is between 0 and 2 pi, that's positive, right? So it's less than 2 pi. That's equivalent to 25 pi over 6 is pi over 6. All right. Couple things here at the end we're going to talk about are more application related. And so we will see some application problems, aka word problems, right? See how this is actually used. And arc length is one of them. Now we've actually mentioned arc length before. Arc length visually is just the length of a piece of a circle. That's the arc length. I mentioned it in passing when we talked about stretching a string and talking about what radians are. Okay? So definitionally, let R be the radius of a circle, and theta is the non-negative radian measure of the central angle of the circle. The area, I'm sorry, I'm reading the wrong one. I'm reading area, arc length. Let me go back up. Let R be the radius of the circle, theta the non-negative radian measure of the central angle of the circle. The length of the arc intercepted by the central angle is S equals R times theta, right here. You do need to notice that the theta is measured in radians. If you put it in degrees, you're not going to get the right answer. It's not going to make sense. So visually, what we've done here is we've said, okay, we've got some arc. It doesn't even have to be in standard position, right, wherever it is. And it's got some measure of the angle theta right here. So there's some radius, there's some measure of the angle theta, and what we're finding is we're finding the length along the exterior. We're finding the length of the crust of the pizza. That's what this is, right? It's the length of the crust of the pizza. So we're going to do a really straightforward one where it just gives us those measurements. So we've got a radius of 16 inches. That actually is the size of like an extra large kind of pizza. When they talk about inches of pizza, sometimes a really big one, right? 16 inches from the radius. And the theta is measured as 60 degrees. Now, in order to find the arc length, the formula is S equals R times theta. But there's something we have to do to this problem before we can just put in the numbers given. What is it? We need to convert to radians. This angle, 60 degrees, is not in radians, and it needs to be to use this formula. So the first thing we're going to do is we're going to take 60 degrees, and we're going to turn it into radians. Now, how do I turn 60 degrees into radians? Pi over 180. You got it. Whoops. Now, the pi is fine, written as pi. When I have 60 over 180, right? What is 60 over 180? It's 1/3. So this is pi over 3. Okay, again, it's fraction simplification. Your calculator can do it for you if you don't want to do it by yourself. Okay, this is pi over 3. So as I'm looking at finding the arc length then, the radius is 16, and the measure of the angle is pi over 3. Written in exact form, this is 16 pi over 3, because 16 and 3 don't reduce. But if I'm also asked to round it, which I am, to 2 decimal places, the calculator is what will do that for me. And I will get 16.76. And I need to use a measurement. A measurement unit was given in this problem. It needs to be my answer as well. What is the unit that I'm working in? Inches. Inches. So the unit on the theta is in radians, but the unit on R was in inches. That's the one we're looking at. So that's the measure, right? This is a length along the crust, right? The crust of the pizza, it's 16.76 inches. Notice it's almost the same, but that's because it's almost, pi and 3 are almost equal. This is almost the number 1. Do you realize that? Pi is about 3.14, and you're dividing it by 3. This fraction is almost the fraction 1. So the idea that we got something that's almost 16 makes sense. Okay? Area. Okay. So have you ever wondered how they calculate the calories in one little slice of the pizza compared to the whole pizza, right? They're doing it using the area of the slices. Okay, so finding the area of a sector of a circle. So a sector, visually speaking, is the pizza piece. So again, we can draw this wherever we would like. And what we're finding is we're finding the area inside. Now, it is still hinging upon the radius. The radius matters. And the angle theta. The angle theta matters. And the theta is still given in radians. Okay, so that's still happening. And this is the formula for the area. It's 1/2 r squared theta. Now, you probably remember the formula for the area of a circle. What is the area of a circle? Yes, pi r squared. Does that sound familiar to everyone? So this is what's used to get this. And I want to show you how, because it's not rocket science. But I'm not going to ask you to repeat it. I just want you to know that these things are not sort of coming out of nowhere. They're not just developing in the middle of the sky. Okay, like they actually come from something that we've already established. So here's the way that this works. So we start with the area of the circle. But we don't have the whole circle, right? So this is the area of my sector now. So the circle area is multiplied then by theta over 2 pi. This is the percentage or the fraction of the circle that's represented. Theta is our angle measure. 2 pi is the measure of the entire circle if you went all the way around. Like if theta goes all the way around, you'd get 2 pi. And if I replaced the theta right there with 2 pi, I would end up with the formula that we have for an area of a circle. And then things reduce, right? This pi is going to cancel out. And I'm going to be left with the angle theta and the r squared that are coming about from here. Now, here's the 2 that still remains to get the 1/2. So things just drop themselves out, they fall out. It's just coming from the area of a circle and doing a ratio of the area. That's what's happening. So let's do real quick this problem. And then we will be done with this lesson. We won't have time for board work, which is okay, but we're done with 1.1. We'll start 1.2 next time. So the formula is that area equals 1/2. Yeah, just undo. 1/2 r theta, r squared theta. R in the problem says that it's 6 yards. Theta is 15 degrees. We did a minute ago this ratio, not with 15 degrees, but we're turning it into radians. It is pi over 12, so we won't go too far off track here. I have pi over 12. So when I measure 1/2 times 6 squared, make sure you're squaring the 6 first. That's 36. And then multiplying by pi over 12. The exact value is 1.5 pi. That's exact. And then a approximation with 2 decimals as requested is 4.72. And it is in yards squared, right? Area is in square units, so this is square yards. It's written as yards squared. All right, so what does it mean since we finished this lesson, because the first lesson we finished? It means that your My Math Lab assignment will be due before you show up in class on Monday. Okay, so My Math Lab section 1.1 is what's due. If you would like to start the quiz practice, you may. If you'd like to wait on that, you may. But we right now have My Math Lab section 1.1 that's due.